So I'll be talking about not that useful quantum advantage, so about sampling, boson sampling, but hopefully in like experimentally realistic regime where the number of photons scales linearly with the number of modes. So it's a joint work with a bunch of people from States and Brazil. So Adam, Sean, and Felipe from Stanford, Daniel brought from Niterói, Daniel from UC Davis, and Bill from Chicago. Right, so yeah, and I'll be just meditating on this specific subject throughout the talk. Yeah, okay, so just to set the stage, right, so we are interested in a paradigmatic boson sampling experiment in which n Fock states enter linear optical interferometer described by some unitary matrix U. They scatter through this interferometer. You get particle number detectors in the output. You have m photonic modes in total. So you record clicks. So input state is, you know, all one states in first n modes. You have output states that just measure, you know, for every mode you count how many particles landed in this specific mode. So if you have more than one particle in a mode, we say we have collision, and we have, yeah, the process is described by unitary matrix U, right, we all like know that, yeah, or we have heard that hardness of this boson sampling comes from the fact that output probabilities in this scheme are related to permanence of of matrices that you get when you what you do when you have output pattern S, you repeat, you take input T, so you take T columns of this matrix. So in this example, first n columns, and then you repeat rows of this matrix according to this pattern S. So S1 repetitions of the first row, S repetitions of the second, and so on. Good. And right, so the scheme was proposed, yeah, like 15 years ago by Aronson and Arkhipov as one of the first examples of like quantum advantage or supremacy based on sampling. And its proposal coincided with experimental developments on the side of integrated photonics. So there were small size proof of principle experiments performed in different groups around the world. And by now, 15 years later, it enjoys strong guarantees for hardness, comparable to random circuit sampling, IQP, or fermion sampling, but with the catch that this works in the, most of the works are focused on something I call diluted regime, in which number of modes is much greater than the square of the number of photons in the setup. Okay, so our work is trying to extend hardness arguments for boson sampling like beyond this regime. So let me compare those two cases for you. So the diluted regime. Here we are in the with just typical outcomes that we observe when we put high random unitary. They do not have collisions. Okay, so we're not gonna have photonic bunching. Okay, so probabilities are given by permanence of simple submatrices of a matrix. Okay, all output states you can permute, collision-free states you can permute to each other by just shuffling modes. So all of them are equivalent, and you have property known as hiding. And lastly, if you maybe have even greater number of modes, n cubed, you can approximate this submatrix by suitably normalized just Gaussian, complex Gaussian matrix. Okay, so those are technical properties that Aronson and Arkhipov used in their original proof. But what's the situation in the saturated regime? So it's much more complex, because right, typically you do get collisions, so photons bunch in the output modes. Furthermore, right, like you don't have just permanence of submatrices, but permanence of submatrices with repeated rows. In this case, you have many inequivalent types of outcomes, like different bunching patterns. You cannot map them to each other by just applying shuffling permutation of modes. And lastly, entries of the submatrix, or entries of this matrix whose permanence you need to compute, are correlated, because it's a big submatrix of a unitary matrix. So this is on the technical side. And I just mentioned that, extending our original arguments to this regime was put as one of the open problems by Aronson and Arkhipov in their work. Right, and also other schemes based on photonic sampling. They work also in the diluted regime, not in the saturated regime. Okay, and moreover, on the experimental side, you can actually, see, I collected for you maybe freshest experiments. That we are really in the saturated regime experimentally. So having many very big interferometers compared to the number of particles, it's not where experimentalists are nowadays. So here you have some type of, actually it's like a quench experiment in atomic, it's like atomic boson sampling. Right, so ratio between the number of modes and number of particles is like 5. You had more efforts on the side of Gaussian boson sampling, but even the newest result from Hefei from 1 month ago, number of probably detected particles is for the 3,000, a number of modes. I think they did time multiplexing, if I remember well. It's still constant. Constant. It's the ratio is 2. You see. Okay, so what we aim in this work is to push. So first we give careful combinatorics of collisions in the saturated regime. Second, we try to give complexity-theoretic arguments for hardness of sampling when the number of modes scales linearly with the number of photons, under some mild constraint, roughly number of modes has to be at least twice the number of photons. And we have a version of that also for a variant of GBS or scattershot boson sampling. Good. So first, combinatorics of collisions. Let's look on just expected outcome probability when we fix input and output S and take a higher average over unitaries here. So it's actually very easy to show, bosonic subspaces an irreducible representation of a unitary group that expected for every S, expected probability is just 1 over dimension of the bosonic space. So expected probability amounts to just sampling S uniformly at random for all possibilities that you have. Good. And now some property that we are after is number of clicks in the output. So number of modes that for which we have more than 1 particle in the output. Okay, so I call it number of clicks. How many detectors clicked at least with 1 photon? And right, you can you can analyze this probability distribution and actually give like asymptotic formula for the expected number of those clicks. So if alpha is the ratio between number of modes and number of photons, and is kept constant, the expected number of clicks would be still proportional to the number of photons. Okay. Moreover, like you can give concentration of measure argument, concentration bounds for the number of clicks. So you have exponential suppression outside of this mean. So very likely you're gonna randomly chosen S, according from flat distribution of all possible outcomes, will have extensively many modes occupied, and then you see it like how it changes with different with different ratios. So as the ratio right, so it's what is the fraction of outputs that what is the ratio between number of clicks and number of photons? So as alpha increases, this so number of modes increases, this moves to 1. Okay, but it's still extensive for constant ratio. Right, and maybe for the purpose of the talk, what is important is that we are gonna, as you do this experiment, you're gonna probe your output probability would be probing just submatrices of extensive size. Okay, even when in the saturated regime. And now, just moving to hardness. Okay, but maybe there are some questions at this point. I'm happy to take any. Okay, it's very elementary so far. This number of clicks would be, would be sort of like a measure of hardness for us later. Mm-hmm.
So for your first expectation, I guess it's easy to calculate that, but it's also a bit surprising, no? Because the input is 1 photon per mode.
Yes.
Right? And so then if you apply a unitary to it, the states of different occupation matter that aren't unitarily equivalent. No? Is there some kind of intuitive understanding why the expectation there still comes out flat and does not distinguish between?
No, I mean it's flat in the base in the for all basis elements. Okay, so it's not like flat. Okay, for me the intuition would be it's just one design. Okay, like it's unitary one design in this space. Okay, so I just express this, as just matrix element of this representation as we move from T to S, two basis states. Yeah. So it's so it's very right. Although different types of S would have different weight, and then as you tune M very large, collision-free guys dominate. Good. So moving to hardness of sampling. Jens already mentioned it. That's some in one of maybe in 3 sentences. I spent probably more. Right. So I am just gonna assume that I have access to a classical simulator that outputs samples from probability distributions QU. And this probability distribution is beta close to the true quantum probability distribution P, and I'm supposed to do it in polynomial time, in the parameters of the problem, and I want to refute existence of such a sampler, and now in the course of our analysis we came up with a very interesting problem called super. And we named super. It calls from subunitary permanent estimation with repetitions. So the problem is to estimate permanent of a matrix V for V, which is chosen US, where U is her randomly chosen, and S is random output pattern, okay, that you get from uniform distribution over all possible basis states. And we are supposed to do it with some additive error, epsilon, that can depend on S, on the output, and with high probability over the randomness. Okay, so that's our problem that we needed to consider. And right, and it arises because from just assumption that you have classical simulation algorithm with, say, inverse Pauli precision beta, you can apply this reduction based on Stockmeyer approximate counting algorithm, but crucially we don't need hiding because like different outputs are not equivalent. So we get that, like within like third level, in this complexity class, BPP to occur to NP, we can solve this problem, this super problem with high probability and this error tolerance, okay? Like exponentially small error tolerance, right? And we don't need hiding, but like because of that, we like in the definition of super, we don't have specific output, but we have random output S here. Good, and then just like with other quantum advantage proposals, you can now conjecture that it is, let's say that solving the super is sharply hard for parameters that we care about, so for in the saturated regime. So when you do it, you get collapse of the polynomial hierarchy, okay? Like just like with any other quantum advantage proposal, we cannot prove this like we can just give evidence for this. We cannot prove this conjecture. We can prove just evidence for this conjecture. Okay, so this is what the next slide is about. So right, so we prove that it is sharply hard to solve this super problem with this additive accuracy to the error which is like smaller, okay, than what was in the previous slide, what is needed for the conjecture. So it's like x n log n, okay? Right, so it's evidence for the conjecture, not the proof of it. Right, so shaving off this log factor and constant factors would amount to like proving the conjecture, and thus sort of unconditionally proving hardness of sampling. But yeah, we are not there. Okay, so what are the key ingredients when you do the reduction? So first, we actually have, as I said, many output types. So we actually first prove that for random S, it is hard to, sharply hard to compute permanence of binary matrices, but those binary matrices, they are, they sort of mimic the structure of matrices that you get from this boson sampling experiment. So they are, you have number of cliques here times the number of photons, okay, and then so you take this matrix which has sufficiently many rows and columns, and the number of rows it corresponds to cliques in S, and then when you repeat its rows according to pattern S, this quantity would be then like hard as long as in this regime, okay, like for random chosen S. So that's first ingredient. The second ingredient that I'm just gonna touch here is, we need to do worst to average case reduction. So to just from being able to solve this super problem, okay, with those parameters, we need to then extrapolate it to being able to solve those sharply worst case instances. So to do it, we do polynomial interpolation. So we interpolate between suitable, between high random matrix, okay, and or high random submatrix, and this worst case matrix that we care about. So without going too much into details of the proof, but what is sufficient for us is to have the following result. Like if nu is a probability distribution of this n by n submatrix of high random m by m matrix, when we now perturb this distribution by taking convex combination between this high random submatrix and binary matrix X, that corresponds to roughly this worst case A. We can prove that the total variation distance between those two measures, okay, is bounded in parameter t and like this. Okay, so it's needed for polynomial interpolation argument, and to do this we study actually probability distribution of the density of the submatrix. So in this regime it actually has full Lebesgue density. We need to analyze it, and we also need to understand quantitatively norms of the submatrix. Good, and then we go through machinery of polynomial interpolation. That was developed in earlier works, for example, in this work by Adam and others. Okay, so robust Bergkamp-Welch theorem is the key here. So how am I doing with time? 5 minutes? 5 minutes, yeah. Good. So just maybe sketch of the of this worst case hardness. So we can actually show that permanence of matrices with repeated rows are still are hard to compute. So the idea is that you can, assume you want to compute permanence of a C by C matrix. Let's say you can think that the C is the number of cliques in S. Then I can construct algorithmically this the C by N matrix A that has the property that if I compute permanent of its version with repeated rows, I'm gonna get something proportional to permanent of X. So just maybe in a simplest example, assume I want to, like 2 modes, 5 particles. I want to compute permanent of this X. I can now append ones and zeros to its rows like this, so that if I now repeat rows of this matrix A, and compute permanent, I'm gonna get something proportional to permanent of X. Okay. What is important is that for generic outputs, this C is extensive in the number of particles. So we can like for many output for many outputs we have worst case hardness. Okay, sort of simultaneously. So this is and we argue that number of clicks is therefore like proper measure of hardness. Not number of photons only, because when you have few modes, many photons is classically simulable. If you have very few photons and many modes, it's also not hard, so C is the important thing. Okay, I don't have time, but we have version of those problems for scattershot boson sampling, in which you, instead of single photons, here you have 2 mode squeeze states, and half of the modes they go through a random interferometer, half of the modes just get detected without any any coupling. And we have a G super problem that has the same role as previously super problem. Good. Okay, and we have analogous evidence for hardness of sampling from this more experimentally, let's say, accessible setup. Okay. Okay, so that's the conclusion. I sketched that. I presented careful combinatorics of collisions in the saturated regime. So we go beyond like bosonic birthday paradox and the diluted regime. We have fairly strong arguments for hardness in this experimentally relevant regime that match other hardness arguments for quantum proposals. We have a variant of that for GBS. Right, and like something which is fine that I want to advertise. I didn't have time to talk about it at all, but funnily enough, we don't have this work out yet, but together with Zoltan and his students, we actually can prove anti-concentration for boson sampling in the saturated regime. Just second moment is enough to prove hardness, okay? In the diluted regime, it doesn't work. We can also give computable formulas for like average cross-entropy, linear cross-entropy benchmarking scores. Right, and maybe with that I conclude. Thanks for your attention.
Questions for Michał?
So I guess it's too fine-grained to actually prove it, but if I ask you for your assessment, what is harder to actually do, the saturated or the non-saturated, the diluted regime? What's harder to simulate?
To simulate, I mean, if I probably take state-of-the-art, there are some state-of-the-art like methods. I think when you have such, it's slightly easier to classically simulate. There was some follow-up, some work by Clifford and Clifford, but other Cliffords that sort of studied this. It's still exponentially hard to simulate. Yeah, I'm a symmetrist. I don't know, like here, like which I prefer maybe group theory than I come from like this this part of community. So the saturated regime is more sort of interesting for me because things they have intricate properties due to group theory, and yeah, so I maybe like it more.
Thanks for the talk. Of course, I know how these constant errors come in through the Stockmeyer machinery and so on. I mean, that goes without saying. But is there any hope to have like a hardness result that can accept slightly more than constant errors in the total elevation distance? That before is like classically simulatable? Because I mean, a constant error is like very demanding still. Like I mean, per component means like 1/n.
Right.
Fidelity or so. I mean, it is what it is. I'm not.
Yeah.
But
okay. Personally, in this context, I am not a big fan of total variation distance because it's not computationally. You cannot like verify this, as you very well know. So perhaps one possible way would be to look at different metrics in probability space that are maybe more like that are like easier to experimentally like verify. I don't know. Yeah, sorry, I cannot.
One final question for Michał, if there is. No questions, then let's thank him again.